Alrighty, folks. So today we are starting a new topic, investigating the Earth, and it's a hodgepodge of things. I won't lie to you. A couple semesters, I found myself getting all the way to the end and talking about stuff that was going to be on the final, and said, of course, the layers of the Earth diagram will be on there, and they just blinked at me, and I mentioned a few other things, and here I realized that because a handful of these things you just ought to know about the Earth if you're taking a Earth science class, and geology being an Earth science class, Earth science being obviously an Earth science class, it just didn't come up in the lecture about minerals or plate tectonics or volcanoes or earthquakes, all those chapters in there. And it was in the stuff was like sort of in the introduction, which I don't know about you, but I always skipped over, as a student at any rate. So I put this lecture together little by little over the years. And like I said, it does jump around a good bit. All this stuff is in your book, but it's in the introduction. It's a little bit in chapter, I'm going to make up a number, 17. It's in 5. It's bits and pieces sutured together that kind of gives you an overview of stuff we got to get down, stuff we ought to know, how old the Earth is and why we know it, for example. Okay? And that way, if we don't ever get to it in other chapters, then at least we've covered it. Sort of my goal here. So for you chapter readers out there, bear with us. The time is coming where you will actually be able to say, okay, today we're talking about chapter 3. We're going to do minerals, and just minerals, and that has its own chapter. Volcanoes has its own chapter. That time is coming. We aren't there quite yet. All right? Like the protons and neutron stuff, that was in probably an appendix. Okay? The nature of science stuff, that was in, again, the introduction. So we're hopping all over the book. But I promise that will end soon. We'll actually do just, one chapter at a time. All right, so what have you been staring at while I'm talking to you here? Other than your phones. The Earth. Yeah, picture of the Earth, right? All right. What's all that blue stuff? Water. Good. Good. The green and the brown? Land. All right. You may have heard this. They call us the blue planet. Okay. This is why. All right. Nearly 3/4 of the surface of the Earth is covered in water. And this is a great example of that. Now, if they had showed you the other hemisphere, the other side, you might be like, I don't know, that looks closer to 60-40. But this is a great picture to convince you that it's 70-30. It really is. You got to do the math. But like I said, if you look at the other side, it's a lot more land mass there. Between Eurasia and Africa, takes up a good chunk of everything. So, what's that white stuff? Clouds. Good. And where do the clouds live? Atmosphere. Excellent. Good. So we know some words. That is excellent. In your previous science classes, high school, middle school, you might have used the O-spheres. Hydrosphere, atmosphere, there's biosphere, this sphere, and that. Yeah, well, troposphere, good one. We will actually use troposphere. I'm not a huge fan of dividing the Earth into these life spheres, these zone spheres, because a lot of them overlap. And again, at least as a student, I found that a little confusing. We can't obviously not use the word atmosphere. We have to say that. And when we talk about the atmosphere, we're going to say troposphere, stratosphere. There's a handful of those. But I mean those bigger, more generalized spheres, like I said, the biosphere, the hydrosphere, and a handful of those other ones. So we're not going to go down that road if you remember those words. If you don't remember those words, completely ignore the last 30 seconds. So we got water, we got land, and we've got an atmosphere. That's pretty much all we need to make a planet, right? At least as far as we're concerned. Is this a real picture? Well, let me rephrase that. Could it be a real picture? You should not be a thinker, folks. Can we get a picture of the Earth? Yeah, okay. We have that technology nowadays, all right? 100 years ago? No. All right? Not that long ago? No. But nowadays, yes. I just updated one of the slides. 1958, we sent our first satellite up. To my knowledge, it did not have a camera on it. It had a Geiger counter and a tape recorder. Probably some other stuff. But so, if you were taking this class like when your grandparents were in school, we didn't have such good pictures then. Depending on how old your grandparents are, not at all. My parents were in high school in the 50s. So they probably didn't see a picture of the Earth when they took science class in high school. But yeah, now it is. All right. I only ask this because we take so much for granted nowadays, and at some point we might show you a picture of the galaxy. All right, and I'll say, "Is this a real picture?" Well, yeah, it's a real picture. Well, no, we can't back up far enough to get a picture of our galaxy. We do have pictures of other galaxies. All right, and we're pretty sure we know what kind of galaxy we live in. Spiral. So we take lots of pictures of spiral galaxies. So oftentimes when you see a picture of, they're talking about the Milky Way, that's our galaxy, right? They'll use a real image, but it's not us. We can't get that picture yet. Probably. I don't want to say ever. Ever is a long time. But it's going to be a while. So what's out there? We already talked about the atmosphere. We're going to go a little further than that. The easy answer is what's out there is space. All right, and well, what's space? Space is a lot of stuff. Space is where the other planets are, maybe in your mind. Space is definitely where the other stars are. As we're going to find out a little later, space is a little closer than probably many of you thought. I was surprised. We got something called the magnetosphere, the magnetosphere. I like to say neato. So we got the magnetosphere. And in the magnetosphere, we've got something else out there that's important called the Van Allen radiation belt. You've probably heard about the magnetosphere. Probably not the Van Allen belts. And again, when I change slides, please rest assured that you have access to all these on D2L. Hey, I didn't say the last word. And you'll also see these words again on upcoming slides. This isn't the only time. So if you're still writing this down verbatim and I switch slides right now and you don't get the last line, you will see it later. So the magnetosphere, what do you know about it? We know that it is created by the core of the Earth. All right. The inner core, the core is split into two. We've got an outer core and an inner core. Kind of picture an egg inside of an egg. Not the shell, but the clear goo and the yellow goo. All right. The yellow goo, the yolk, is, in this metaphor, going to be solid. That's the solid core of the Earth. All the stuff around that remains molten. All right, liquid may be a stretch of a word, but molten is a good word to use. The problem is pressure. Some of you have had chemistry, some of you haven't. You know that liquids under pressure behave really, really weirdly. Okay? So we're going to, most correctly, we should say it is molten. because the Earth spins, that molten material sloshes around the solid material. They're both made of primarily iron, a little bit of nickel and some other stuff thrown in. But that creates an energy field. That energy field, just like a battery, has a positive side and a negative side, or what they call polarized. And that gives us our force field, if you would. It's an energy shield around us. It doesn't stop spaceships from coming in like in the movies or anything like that, but it does stop some other rather important stuff, or we would have never evolved to this point in life, more than likely. It's responsible for stopping a lot of the sun's nasty stuff, energy that we don't want from the sun. Here's a very cool picture of it.
It's like a big spider.
It does. It does. One of my favorite albums is The Rise and Fall of Ziggy Stardust and the Spiders from Mars. And if that ain't a spider from Mars, I don't know what is. But, or a giant space squid, right? Could be a giant space squid.
It's like one of those deep sea squids. It's got the super long tentacles.
Yeah. Yeah. 5. Unfortunately, it's got 10 legs, so kind of gets rid of the spider thing. But still, Mars spiders could have 10 legs, right?
Is that how like the northern lights are created?
Yeah, not exactly. And that's something I should know more about. That's extra energy plasma and gases in the atmosphere that get trapped, but where exactly they get trapped, I'm not sure. Yeah, that's the part I'm not sure about. But yeah, it's sort of connected. This is out there fairly far. I want to say the northern lights are trapped a lot, the gases are trapped a lot closer, but don't quote me on that. I should know that. I've never actually seen them. Whenever we're supposed to be able to see them, of course, you're either get cloudy, or I'm somewhere where it's too bright. So I have seen the galaxy. You can see that on a really dark, clear night. It's just a white sort of cloud if you look in the right direction. But I haven't seen the northern lights yet. So what we got here is it's a little deceiving, mainly because we all think of a giant space squid or whatever coming in. Remember, the Earth has a North Pole and a South Pole, and I'm trying frantically to get my mouse that I can't see. Where's it on there? All right, I'm going to just look at the screen instead of the projector. So remember North and South Pole. So where it pinches in here, those are actually your North and your South Poles. So this is one hemisphere, and this is the other hemisphere. It's drawn out on the away from the sun side because of that. The sun's energy is pulling it out, dragging it out. All right, and again, at some point this was probably theoretical. Nowadays we've got satellites up there measuring God knows what. I'm sure they've supported this idea. This was somebody's thesis project at some point, whether it was a dissertation for a doctor or master's thesis, I don't know, I forget. But someone was working on this. And you see a explosion coming from the sun there, jetting out some energy. We hear about those because, God forbid, it messes with our cell phones and whatnot, solar ejections and whatnot. But there's a lot of nastiness we don't want from the sun. Various different wavelengths of energy. So the magnetosphere is very helpful for that. It's also, and I should have a slide about this, but I don't. As I implied, there's a positive and negative. That's our North Pole, South Pole. We know from looking at rocks on the ocean floor that have been pretty much sort of continually made, conveyor belt style, over the last several 100 million years. Every so often, the polarity of the Earth shifts. Positive becomes negative, negative becomes positive. We know that because just like if you had little iron filings in front of you, and a magnet you'd play and they'd move around, okay, they respond to that. Well, the iron in the rocks before they cool also responds to the magnetic pull of the Earth. So what we see are the iron molecules. We'll just say it's not a molecule, but it's probably iron oxide. That is a molecule, I guess. The irons orient themselves, for this one band, all in a north-south direction. Let's say normal north-south. Then there's another band after that that represents another period of time when that is switched. And then it goes back to this and back to that. They're working on that. Again, that's what the data shows them. But if we just sort of explain to you that the polarity is a function of the Earth rotating, right? We told you that it creates it at any rate. It would seem to be that at least in my simple mind, that it must be the direction of the Earth that creates said polarity, the direction of the rotation. Well, obviously you can't stop the Earth and start it rotating the other way. I don't think you can at any rate. So they're not sure why we're seeing this reversal of polarities. But we've got record of it happening dozens of times. It's also not tied to any mass extinction events. We've got records of those, of course. And that was my first question when I heard about this. Surely that's going to mess up all the critters on the planet. Not just the migrators, but you've got iron in your blood. All right? And, it's used to the last 20-some years of north being north and south being south. And it does respond to the magnetics. So, yeah, I don't know.
When's the last
and they
time
don't know.
polarity has changed?
Within the last, this is why I need a slide. They say we're due for one. Put it that way. Yeah, we're due for one. But again, no record of mass extinctions. North Pole's been flipping out. You guys may or may not have heard of that. It's moving like crazy. That always has been. All right. That's why compasses all have that little screw on it, so you could adjust. It's called declination. You'll learn about it when we do topographic maps. You can't use a map from gold rush days, okay, with your compass today without adjusting your compass to back then, or you'll end up way off. Now, of course, the farther north of the equator, the farther south of the equator you go, the more that matters. Yeah, nonetheless. But yeah, the North Pole's been moving a lot more frequently and irregularly than they're used to. So I don't know if that is leading up to anything. Be interesting. We'll see. So magnetosphere, neat stuff. It's still, as I'm indicating, still don't know that much about it. All right, here's the slide I just added, and I apologize. It's probably really hard to read. This is the Van Allen belts. The slide's been here. I just added the pretty rainbow colors behind it. So as I just said, 1958, we discovered the first satellite, and they were apparently quite surprised to find as much radiation as close to the Earth as they did. But they sent a Geiger counter up, so they were obviously, expecting something. And there's two rings of this. It's a little kind of obvious here. It's a little more obvious in the next picture. There are areas within the magnetosphere that have trapped incoming solar radiation. So we told you that's what the magnetosphere does in the previous slide. It traps incoming solar radiation. Now we're telling you that those places have names. All right? Called the Van Allen radiation belts after Dr. Van Allen. So the outer ones, the outer ring, is the trapped by the incoming solar radiation. All right? And it said that the inner belts was formed by the radiation interacting with the atmosphere. So maybe that one is where the northern lights are. All right, on the inner belts. But again, don't quote me on that one. You've also probably heard, if you pay any attention to space travel, that one of the things we have to worry about is exposure to radiation. Okay, if you've watched any sci-fi movie, if you paid any attention to one of the many reasons we're concerned about the folks on the space station, there's a lot of radiation bouncing around up there. It's because we have the magnetosphere. So but that's good, okay, because we didn't want all that coming through and actually bombarding the surface, right? It just makes it a little more dangerous to be out there. So, and that's fine because we could shield ourselves, we could protect ourselves, build extra stuff into the space stations and whatnot to help us shield from that stuff. So here's another image of the belt, much less colorful. I thought that one was pretty fun. All right, so that's further out in space. Let's get a little closer now, and we'll talk about what we know and love, our atmosphere. It's got a lot of names: gaseous bubble, envelope. I've heard a lot. I like bubble because, you know, Earth is round-ish. Bubbles are round, so that's a good way to go with that one. But envelope works as well. It's encasing or sealing in the Earth. This one catches a lot of you by surprise, this first little bullet here. 78% nitrogen. All right? You're like, wait a minute. I thought oxygen was the most important gas. Well, it is the most important gas, but it is not the most common gas in our atmosphere. All right? Right now, as you suck in some air, you're taking in 3 times more nitrogens than you are oxygens. Roughly speaking. Again, that geologist rounding math there. There's other stuff. We're going to see it in a minute. The atmosphere is held to the Earth by the Earth's gravity. All right? And that's really important because we need an atmosphere. All right? And when we get a little later in this conversation, we're going to talk about that we didn't always have an atmosphere. You're going to say, well, wait a minute. We've always had gravity, right? If we've always had gravity, why haven't we always had an atmosphere? Well, there's a reason. I'll tell you that. Just dropping a couple vocab words here. The ozone layer. Somebody tell us, what's so awesome about the ozone layer? Do we like the ozone layer? Ozone good. Ozone good when it's in the stratosphere, yes. What does it do for us?
Probably blocks some radiation.
It does. It helps block radiation for sure. Stuff that sneaks by the Van Allen belts, all right, for sure. It blocks ultraviolet radiation, which again, if that got through, not good. UV is the stuff that they warn you with skin cancer and all that. Okay. UV rays, not the best stuff. We haven't always had the ozone layer. It had to be made. We'll talk about that too. You heard of smog? Yeah. Smog is ozone at the surface, also made, but by combustion of fossil fuels. In larger cities, in really hot temperatures, they sometimes have what they call ozone alert days or ozone awareness days. And you're not supposed to fill your car up during the sunlight hours. You're not supposed to touch grass till the sun goes down. A handful of things just to try and stop the smog from building up. When we burn the fossil fuels, gasoline, oil, coal, whatever you want to call it, it releases, ozone is O3. Really close to oxygen, which we love. Oxygen's O2, right? It releases ozone, and because of some atmospheric conditions when the weather's like that, it can't escape, and it just builds up and builds up and builds up, and maybe you've seen pictures of LA. LA is a great place if you want to see smog. Manhattan gets it too, but LA's is, you can literally see a haze cloud over the city sometimes. But generally speaking, yes, ozone good. And we got to throw out one more vocabulary word here. I think one of you already dropped it this morning. Troposphere. Troposphere is the portion of the atmosphere that we live in. Okay? Stratosphere, just FYI, even though you'll see it again in a minute. It's just above the troposphere. big deal a few years back. One of those crazy Red Bull stunts. They had somebody free jump from the stratosphere. They made it down alive, if I remember correctly. But it was a hell of a thing. They needed a special suit, and think about just when you fly in an airplane, all the pressurization and whatnot that they have to adjust for you. So that was a big to do. Okay, a couple equations, but I'm not gonna ask you to remember these equations. They're here to show you how stuff is related, connected. We have two words here, two vocabulary words, and then equations to sort of help understand those vocabulary words. Air pressure and air density. Okay, those are the vocabulary words. Air pressure is, strictly speaking, it's the weight of the column of air above you. Okay? You, again, probably know this, but you were surrounded by not just void, right? There's air all around you. You move your hand and you feel that cool sensation, okay? That's the air particles zooming by you. Well, if you're just sitting here as you are now, static, you've got a column of air above you, and it goes up to the top of the atmosphere. Let's not imagine that we're in this room here for a moment. It's kind of hard to picture. You guys remember those pin box? I'm sure it has a name, but I always just call it the pin box. It's a little plastic rectangle with, we'll say, a couple hundred little metal nails in it, and usually when you walk by, it has the impression of somebody's middle finger in it, but it just moves to your hand. Okay?
One of those, yeah.
Yeah. So imagine that you're literally walking through that anytime you're moving outside, wherever, except it's air molecules, not pins or nails. All right? So literally, the height of the column of the air above you has mass. It's particles. It's molecules. Come on in. All right? So because of all that, it has mass, and that makes pressure. How do we know that? Well, that silly formula right there. Okay? Pressure equals force over area. Who remembers the equation for force? I didn't throw up this, so I didn't want to scare you guys with too many equations. F equals F equals, come on, somebody remembers.
Mass times acceleration.
Yeah, F equals ma. All right? So the force is the mass. That's where the connection is. What's the acceleration? It's gravity. What, 9.8 meters per second squared, something like that? All right? So you have the mass of all those air molecules above you pressing down on you. And yeah, did you need any of that to know that there's air pressure? No, you didn't. But now you know why there's air pressure. In a minute, you're going to know why there's less air pressure at the top of a hill. Well, maybe some of you could even tell me already. Why is there less air pressure on top of a big mountain than there is at the bottom of a valley?
You're farther above the sea level? Farther into the atmosphere?
Yeah. So strictly speaking, there's less what above you? Air, yeah. It's just you're higher up. You were right, but when we needed the why, you were right. All right. So yeah, there's you're just higher up in the atmosphere, so there's less air pushing down on you. That's why your ears pop. You wouldn't think it would make a difference, and it's not a big difference. But think about it. You're pressurized, just like that airplane cabin is. That's why sometimes your sinuses really hurt, or as I said, your ears pop. We are pressurized objects. We're set up for one atmospheric pressure.
Just like the deep sea fish that get like depressurized when they come up to not high sea, whatever the opposite.
Come to normal. Yeah.
They become like they just like
exactly, and oftentimes just explode too. Yeah. Those critters. If we went down into the ocean, to what he's saying, it's worth talking about here. Again, you may know that if you're a deep sea diver, you need to pressurize your suit, or submarines are pressurized. That's because of the weight of all that water. Water pressure is way greater than air pressure. All right, why? Because more mass. So these critters that live in the deep crevices of the ocean, they actually have as much internal pressure pushing outwards as there's external pressure pushing in, just like we were just talking about you and your sinuses. So when those poor critters come up here, and we did this, we were so excited that we found critters at the bottom of the ocean, we didn't really think about the pressure. When we got them up to the surface, the poor things, they didn't last long.
Yeah, the blobfish is like a deep sea thing that's got brought up to land. It doesn't really normally look that ugly.
Yeah, I don't know the blobfish, but I always picture a lanternfish when I think of deep sea nastiness, but I'll look for the blobfish later. All right, lest we digress. So that's air pressure. Air density. Why do we tell you that we have an atmosphere? What holds the atmosphere here? Gravity, okay? And again, I don't know how much you guys remember from your other science classes, but the closer you are to an object that has a gravitational pull, the more you're affected by it, all right? So, and this goes into your tractor beam from Star Wars or whatever, just its mass, its gravity. So the closer you are, the more effect it has on you. So what we're saying is that this atmosphere is a lot denser near the surface than it is the farther you go out. And again, you knew that because, again, it's hard to breathe. You think about these Sherpas and these folks climbing Mount Everest and everything. They need oxygen tanks. Not because they have asthma, not because they smoked for 30 years, but because the air is really thin up there. You go to Colorado, even, some other really high places. It takes a while to acclimate. All right? The air is legitimately thinner. All right? And that all just kind of ties in here. The atmosphere is not uniform. Not uniform. And it's what I still find, and I know all this stuff, okay? I've known it for years. I still find it amazing that just driving in my car going up what isn't really that steep of a hill is enough to throw my interior pressures off and make my ears start popping. Airplanes, I can see that. That's, they're high. But it matters. So again, you don't need to have these formulas in your memory. You don't even necessarily need to understand them, but for those of you that said, oh, I kind of see that, perfect. All right, that's all we were hoping for, to show you that pressure and density and mass are all related. And remember, there is particles out here in the air. It's not just nothingness. All right, here's a little graphic. Kind of talks about many of the things we've been mentioning. Two points. This is actually a question on the test. I forget if it's split into one question or two. So we just told you that air density decreases with altitude. All right. Air pressure does as well. They both decrease with altitude. And we just explained to you why that is the case. As you see in a moment, that's not true for temperature, which is why we're making a point of it. So there's Mount Everest. We were just talking about it. There's airplanes flying. We were just talking about them. And I'm glad none of you asked me at what elevation they fly at, because I don't know. It's right there, though, thank goodness. Unfortunately, it's in metric. But that dashed line there is the reason I like this picture. All right, 50% of our air is right at about, we'll call that 5,500 kilometers-ish there. It's not quite the middle of 4 and 8. It's a little below the middle. So not quite 6 kilometers up. How many miles is 5.5 kilometers? 3.42 miles, according to Siri. Many of you drove farther here today than that. All right. Yet if you went up, like from here to the mall, you'd need breathing apparatus. Most of us. Kind of crazy. Especially when we're used to jutting about the surface of the earth As long as you got gas money, you go wherever the hell you want. But you go up, you go down, things change really quickly. So anyhow, air density and air pressure decrease with altitude. Don't forget that. All right, we've talked about this. I don't want to dwell on it too much, but we do want this number. Because I did mention 1 atmosphere, okay, and I mentioned those little pins in the pin box thing. So it's defined as a 1-inch square and as high as the atmosphere, all right? Weighs 14.7 pounds. That's atmospheric pressure, 1 atmosphere, all right? You don't notice the 14.7 pounds because you've been exposed to it as long as you've been alive. You don't notice it because your phone, when you pick it up, is also exposed to 14.7 pounds. No matter what you do, you're lifting at least 14.7 pounds. Moving through air. Now, they don't mention that in the weather. In the weather, you're going to see inches of mercury. That's what that Hg is. That's the barometer. Okay? And one of these days, I'm going to take a sabbatical and study barometers. They're just really bizarre in my mind. What it boils down to is that we've got just picture a U-shaped tube, okay? And it's filled with mercury, which we don't like to play with so much anymore.
It's pretty toxic.
It's it's fun though. Fun. I grew up back in the days when dads and grandpas still had coffee cans with mercury in the bottom from all the thermometers and whatnot that broke, and mercury switches, which were a big thing. An easy way of making connection and not connection. So you go out to the garage, hanging out with your dad or your grandpa or whatever. They're like, shh, don't tell your mom, come here. What? Pour a little mercury in your hand, watch it go around. Call it quicksilver for a reason. Neat stuff. Really neat stuff. But yeah, make you mad as a hatter. Eventually. And it's bad in our fish too, right? We don't like it in our tuna. But we're doing science, we still have a little mercury here and there. So in this tube, standard atmospheric pressure, somebody mentioned sea level earlier. All right, that's where this is essentially measured from. The pressure from the air pushes mercury up the other side of that U-shaped tube till 29.92 inches. That's just the normal height of mercury. And again, how we arrived at that, I know they tried alcohol, they tried a handful of things. Why we stayed with mercury, I don't know. It seems very antiquated. So when we get the air pressure changes, this isn't a weather class, so we're not going to get into that too much. But you know that pressure rises, pressure drops. We talked about that briefly with hurricanes the other day. Okay. What that means then is that there's more mass, more particles in the air, so that pushes that mercury up a little higher. It might go up to 30. Doesn't move a whole heck of a lot. It might go down to 29.75 if there's less molecules in the air. And there's a dozen different reasons why you could get more or less. Again, we're not going to get into that. But just saying that when they hear that in the weather forecast, that actually is legitimately measuring something. Wind speed's easy to see. You see the propeller flicking around, and you know that, hey, fast propeller, strong wind. Propeller not moving, no wind. But this one, the barometer, that's a real physical device measuring real physical things. So, very cool. So, the point being, okay, at the top of a mountain, you would expect to see lower than 29.92 or higher than 29.92. Everybody. Top of a mountain. Lower. Good. Less air. Less air pressure. Kabish? Good? Kabish. All right. So, we told you that both temperature and, take 3. That while both air pressure and air density decrease with elevation, that is not true with temperature. This red line here, going through this diagram, depicts temperature trend. Don't worry about all the spheres yet. We haven't really taught you those. But those are layers of the atmosphere. Down at the bottom, that's troposphere. That's where we live. Told you that one. We mentioned the stratosphere already. That's just above the troposphere. It's also where the ozone lives. So a move to the left is a decrease in temperature. Again, you knew this. You go up high, it gets cold. All right? Back when I was growing up, those bomber jackets were really, really cool. All right? The leather jackets that they used to wear like in World War II, with the big woolly linings and stuff. They didn't wear those because they were cool. They wore it because it was cold as hell up there. Really cold. All right? They couldn't insulate the airplane. They tried, but it wasn't great. So those old bomber jackets, they had to wear this because it was so dang cold up there. So you knew that, and you maybe heard about if you tried stowaway in an airplane, you could freeze to death or suffocate, and there's a handful of truths and fallacies about that one. But generally speaking, we all know the higher you go, the colder it gets. Well, that levels out when you leave the troposphere and you enter the stratosphere. And then at some point in the stratosphere, it actually starts to increase. And then we hit the mesosphere, goes back down again, even colder than it was before. And then we enter the thermosphere, and you see it kind of ends, but it's ending on an upwards trend. That red line just keeps going to the right, and going to the right, and going to the right. Space is hot. Now, that is contrary to absolutely everything you've heard, right? Cold, hard void of space, and so on and so forth. Well, temperature E profile. Oh goodness, I have to fix that. Got to put that E up with temperature there. While I'm fixing this, you guys tell me, somebody, what actually is temperature? What is temperature a measure of? Other than heat, or lack thereof.
Energy.
Okay, in what way? Yes, but...
The speed at which molecules are moving around.
Ah, temperature. Okay, why can't I do this? I just got to make it a little bigger. Who said molecular speed? Give that man a brownie. Temperature is molecular speed, definitely. And I missed that somewhere along the lines in high school, early college, whenever I should have got it. Because for the longest time, absolute zero made no sense to me at all. What's absolute zero while we're here? It's in a vacuum, nothing's moving, all right? So I always thought it was just so damn cold that nothing could move. Nope. Okay? But if you approach it from the other angle, that temperature is a measure of molecular movement. If molecular movement stops, there is no temperature. You dig? So it's sort of reversed there. So back to space. Space is really, really, really hot. Or so I said. I want you to believe. What do we tell you about the atmosphere? Does it increase or decrease as you go out towards space? Decreases. All right. Do you have to touch a... that's a bad question because you don't have to touch a flame to feel. I was going to ask you, do you have to touch a flame to feel its heat? No. Why not? Because it heats up the air, right? So, bad example. But in this case, in order to feel temperature, you have to touch that molecule that's moving. Okay? And out in space, said vacuum, there's so few molecules. So the sensation is of absolute zero, or a little bit above, technically, because you're not in contact with any molecules. If one of those suckers zings at you, you're going to feel it. You're going to feel it, because it is moving along super fast, hence it is really high temperature. But you don't come across them. So that's why they can say space is cold, but that's also why we can say that that temperature line keeps going up. Okay?
It's cold until you hit something that's like...
Until you find a molecule,
billion
yeah.
degrees.
Yeah, so temperature is a sensation. You know that. You have to feel it. Okay? So, and the same is true, like we said, and really true in the case of these molecules. back to the troposphere for a minute. Come out of space. In the troposphere, we have another vocabulary word. This is why we generally have our first test after we're done with this PowerPoint, because, good Lord, there's a lot of vocabulary words in it. Lapse rate defines the decrease in temperature as you go upwards through the atmosphere. Now, again, for the most part, I'm hardly ever about the numbers. This is one of those cases. I'm not going to put a question on the test that says the lapse rate is 3.4 degrees, 3.5 degrees, or 3.6 degrees. Not about that. All right? I'm more concerned that you know that the lapse rate exists and that it goes down, step up. But if you want to, remember a number like that, go for it. All right, so for every 1,000 feet you go up, it goes down about 3.5 degrees Fahrenheit. And as you saw on the previous slide, this is for the troposphere only. I'm sure folks who study the stratosphere have a vocabulary word for the sudden increase in temperature. But we're not worried about that. So the lapse rate. Decrease in temperature with elevation within the troposphere. All right. Again, not really worried about numbers, except one or two I'm going to dwell on. Please don't cram all these into your head. So these are the layers of the atmosphere in order. Troposphere is at the bottom, stratosphere, mesosphere, the thermosphere, and exosphere, which did not show up on the previous diagram. Exosphere is essentially space. Troposphere goes from the surface to approximately 7 miles. All right, we told you earlier that about 3.5 miles you're past 50% of the atmosphere. Well, that other 3.5 miles will get you to the end of the troposphere. That one you might want to remember. Stratosphere, even though it looked really huge in that diagram, all right, that only goes up to about 30 miles. Mesosphere, thermosphere, don't worry about. Except the end of the thermosphere, because as we said, space, it's not like there's a dashed line up there. It says you have now entered space. Okay, it fades, it blends, it feathered brush strokes, whatever you want to call it. And speaking of which, what is that little tilde there? That little squiggly line in front of all my numbers? Yeah, approximately. Okay? There is no equals right now. This is approximately. Remember, geologists talking to you. 300 miles. So where's space? From what? Here to Buffalo, but up? How far is it from Utica, New York to Buffalo, New York? I'm sorry. Buffalo's only 200 miles. But you get the point. Something that you guys have quite possibly driven over this summer, okay? And you turn it in the other direction, heading up. Very, very difficult. Assuming you had a hover car or something, you know. And we won't even talk about drilling into the earth. But just as hard, if not more so. Where does space end? Who knows? That opens up a whole other can of worms that definitely should have a pint or something in front of you. Because if you want to say that there is a perimeter, there is an outside, well then the next obvious question, if you're at all inquisitive, is then, well, what's on the other side? And well, then you're going to need another beer at that point. So, again, we're just going to stop at oblivion there. Know your layers in order. Don't worry about the numbers. except you might want to remember the first one and the last one. About 7 miles and about 300 miles. Okay, we talked about the atmosphere. We've been talking about the atmosphere. We told you about nitrogen and oxygen a while ago. And you may have done some math and said that that didn't quite equal 100%. You were right. You may continue to do math and find out that we end up over 100%. Again, you are right. But we're not going to worry about the math. So water vapor, very important, all right? Sometimes, like last week, we really, really despise it. We call it humidity, of course. And I'll tell you, it really sometimes feels like it's way more than 3% of the total atmospheric composition, doesn't it? It's like 50% water the other day, I swear. But 0 to 3% water vapor in the atmosphere at any given time. We also have argon, wonderful argon, okay? And argon, you know what, I used to say I don't know what the heck it does. I still don't really know what it does. But I happened to notice one day shopping for windows that they were injecting, we'll say injecting, argon in between the panes of glass in the windows. And we're claiming that it was helping its heat retention and whatnot. So I'm gonna say that it's somewhere in the realm of being a gas we like. Helps keep a little warmth in there. Speaking of keeping warm, carbon dioxide. All right, the big villain nowadays. 0.035%. A lot of you thinking, are you freaking kidding me? As much as they're complaining about carbon dioxide, that is way less than even 1%, right?
Well, I'm sure that would still, cause a big effect because that's on a global scale.
All right. True.
Like you don't need a lot of poison to kill a person.
Well, it depends on the poison, right?
Right.
There you go. Anybody else have any other thoughts on that? I'm not disagreeing. Don't get me wrong. Or not agreeing, however you take that argument. What?
I feel like argon's a lot more dangerous for us than CO2 is.
Yeah, well. And I guess my argument works here as well. The point is, okay, whether the carbon dioxide is a small number or a big number, it's what Mother Nature set it at. Okay? That's the important part. And where she set it at, we have the weather that we have, good and bad. All right? It is a greenhouse gas. Yes, water vapor is a greenhouse gas. Yes, there's other greenhouse gases out there. And again, they're set where she set them. So when we increase it or we decrease it, we're messing with the normal variation. That's
unpredictable results.
That's going to have an effect. All right. We know from ice cores that we've drilled. They trap air bubbles. You've seen bubbles in your ice cubes, right? It may not have occurred to you that you could suck the air out of that air bubble and throw it under a mass spectrometer and look at the composition of that air, but it occurred to somebody else, and we did it to ice, ancient ice. And we've seen that carbon dioxide levels go up and they go down. And when they go down, we go into something called an ice age. And when they go up, we come out of the ice ages. Everything melts. So they ain't making this stuff up, okay? We've seen that it happens. But it is surprising to see that it is such a small number. I agree with those of you who felt that way. But the important thing is, again, that it is the number that it is supposed to be. You don't want to talk about Mother Nature, that's fine. But it's the number that the Earth sets it at. Other. What do we got other? Other makes up way more than that last remaining object there. 0.065%. Other is a whole bunch of things. Nitrous oxide is always a fun one. All right, that's out there naturally occurring. So if you have a happier day one morning and you wake up, maybe there's just a little higher nitrous concentrations in your area. All kinds of things out there. And now I am going to have to look up argon and see exactly. I'm sure I've looked before. There just wasn't anything spectacular that stuck out. But we do have some argon. So that is the current composition of our atmosphere. Switching gears. We don't need just air to breathe. We also need the sun. Again, you knew that walking in the door. You also may know that the sun's energy is not evenly distributed throughout the planet. There are some places that are way sunnier than others and not exactly related, but there are some areas that receive way more of the sun's energy than others. That diagram is on the right-hand side. But first, I want to show you why the diagram on the right is correct. So, this is something you're going to have to do at home. We can't really get it dark enough in here. I used to try. And back then, very few people even had little flashlights, but now you all have flashlights on your cell phones. So we could totally do this, but it's not dark enough. So, later tonight, tomorrow, whenever, sometime soon, sit in a relatively dark room with a white sheet of paper in front of you and your flashlight. Hold it perpendicular over the paper, which means straight up and down. Okay? And that's the flashlight in the back there. You're going to get a small circle, and you might need a helper. We want you to trace the circle, just to help you remember. So trace the circle of light. Then we want you to tilt the flashlight, no particular angle, but make sure it turns into an oval. Okay? And then trace the oval. And then go back and do it again, and this time I want you to pay attention to the brightness. Now, many of you can predict right now which, I'm going to call them both circles, just conversationally here, which circle is going to be brighter?
Small one.
Anybody disagree? Okay. Why is the smaller circle going to be brighter?
It's more concentrated.
Right? Light's more concentrated. You have the same amount of energy coming out in the oval when the lamp is tilted, but it's going over more area. So the brightness is spread out over a larger area. The energy is dispersed over. There's a lot of ways to talk about it, okay? That's what they're trying to show you on the diagram on the right. And you may have thought, of course, that would focus on the equator. I might have drawn this a little differently had I made it myself. But the idea remains the same. Okay? And again, based on your 20-some-odd years of life on this planet, you probably had a good idea as to where the warm weather was. All right? At and around the equator. And the further north or south you go from there, it gets increasingly crappy, if you ask my opinion. All right? That is directly 100% related to the fact that the sun's energy as we go around the sphere of the Earth is spread out where it hits much less directly. Now, this is tilted off the equator to also introduce us to another concept. All right? That the Earth does not spin 100% up and down like you would do a basketball on your finger. I never could do that personally, but I've seen people do it. You may have as well. It actually spins at an angle. 23.5 degrees off of straight up and down, to be correct. Now, all the globes you've ever looked at were tilted. You probably never knew why. Most of us thought it was just so you could actually see whatever you're looking at is easier. because it tilts up nice and puts it right there. I'd like to think that they actually took the time to put it off kilter 23.5 degrees. So because of that, this band of narrowly focused light actually bounces between the equator and 23.5 degrees north and 23.5 degrees south, the tropics. The tropics isn't just a generic word for warm islands around the equator. You have the Tropic of Cancer, 23.5 north, Tropic of Capricorn, 23.5 south. Again, I made it way too far in life not remembering which one of these is which. I'm going to give you a little trick that it took me, again, embarrassingly way too long to learn. It's alphabetical. CAN comes before CAP. I have really bad teachers, maybe. I don't know. But, so benefit from that. And when I ask you on the test to label, which I will, or at least ABC, circle, Cancer is north, Capricorn is south. Okay? Don't forget. So the sun's direct energy bounces back in between those endlessly. 23.5 north to the equator to 23.5 south, back up to the equator, back up to 23 north, back down. And then our light shifts accordingly. You may have heard that sometimes at the Arctic Circle they get 24 hours a day. Well, that's again what they're trying to illustrate to you here. When it's tilted the right way, where it works out. My son was just up in Alaska, way the heck north. And he wasn't there quite on the 24-hour thing, but he was there at a time when it, well past 11, I think he said, it still looked like 6 o'clock here, 7 o'clock here. It was crazy. He's got some pictures, and again, you can't really tell from the pictures, but he's like, honest to God, I took this at 11 o'clock at night. All right. So that is a real thing, okay? And this, again, hopefully explains to you why.
So are the poles so cold because they spend like half a year in mostly
Lack
shadow?
of energy?
Or is it because the material up there just reflects this light more?
Well, it's never one answer, okay? You have albedo, which is the reflectivity of surfaces, and snow and ice have a really high reflectivity. But I would say if we had to pick a number one, I would say it's energy input from the sun, sure. But there's a handful of things at play. It's a good question. Good question. All right. We got to cram this into your head, and I do apologize. Now it is numbers. Okay. This is why sometimes I get rid of other numbers so we can worry about a few that we need to know. You've heard these words before. And we're just going to try to attach it now to some more knowledge. There's a few of us out there. I'm still in my Hawaiian shirt. And if the temperature stayed, I'd be wearing it all year. I don't really care. But it's still summer, damn it. Put away the pumpkin spice crap. Okay? It is still summer until September 22nd. We aren't there yet. We're close, but we aren't there yet. That is the autumnal equinox. Big word, maybe, but you know how to spell autumn, right? So just put an O, A-L on the end of it, and you get autumnal. We're in college now, we don't say fall. All right, so September 22nd is the autumnal equinox. Where's the sun shining on an equinox? Back of the room, anybody? Where's the sun shine on an equinox? Front of the room, anybody?
Is it like the Americas? Is that
No.
the answer you're looking for?
I'm not.
I'm not sure. What?
I just assumed somebody knows this one. It shares the same first 2, 3 letter. Yeah. Equinox, equator.
Oh.
Okay? So, the sun's energy shines most directly at the equator during an equinox. Hence the equal night, noxus night. So, that's supposed to be your 12 and 12. Daylight and darkness. Again, varies latitudinally. So we're going to start there because this is where we're closest to calendrically speaking. All right. And you notice that this is going counterclockwise. So we will go to the left conversationally now. And we're going to move into what season comes next, you guys? After fall comes winter. Beautiful. Good. We know that one. All right. The winter solstice, December 21st, the sun is shining on 23.5 degrees south. So from September until December, it takes those 3 months to move 23.5 degrees downwards. Southerly, I shouldn't say down. So the majority of the Earth's, the portion of the Earth that is receiving the most direct sunlight in December is the southern hemisphere. You may have heard that the seasons are flipped, right? For hemispheres, when we have winter, they have summer. When they have summer, we have winter. This is why. This is our winter. We're still getting sun's energy, of course, just not as much. So the winter solstice, we don't have a fancy name for winter. As we move from December 21st to March 20th, we're moving into spring, right? I grew up not too far south. I'm from Ohio, which I never considered the South. But in March, we actually got warm weather, believe it or not. Yeah, because that's when spring's supposed to start. I got issues with Utica and its seasons. Don't get me started. Again, latitudinally speaking. So, this is the new word again, vernal equinox. So your equinoxes have funky names. You got autumnal for fall, vernal for spring. V-E-R-N-A-L. Where's the sun shining on the vernal equinox?
Equator.
Yeah, faster guys. Yeah, equator. Doesn't matter which equinox it is, it's still an equinox. Sun is on equator. For the next 3 months, the sun continues its journey northwards till it reaches 23.5 degrees north. At the summer solstice, and then from there, he starts shining further and further south, back to fall. Over and over and over and over, if we're lucky, again. Some things we can tie to this. Your days lengthening, your days shortening, right? So as we move from the longest day of the year, summer solstice, for northern hemisphere. I'm speaking northern hemisphere, okay? If any of you are from the southern hemisphere, I apologize, but we are northern hemispherocentric in this class. That is the longest day of the year. You move through, you've probably noticed it's no longer nice and bright at 8 o'clock anymore. It's because we're practically to the equinox here. And as you move into December, holy cow, right? It starts getting dark, what, 4:30 stuff. Then as we move into spring, your days start lengthening and lengthening till you get to the summer solstice. Oh, by the way, winter solstice, I don't know if I just said this or not, shortest day of the year. Okay. Questions? All of that is because of the tilt of the Earth, okay? 23.5 north, 23.5 south is because we're tilted off of center 23.5 degrees. If we were tilted 17 degrees for some strange reason, and not that 23.5 isn't strange enough, but if we were tilted 17 degrees for some reason, well, your tropics would be 17 north and 17 south, and we'd probably, see, I'm not going to make predictions, but things would be different. If we weren't tilted at all, we wouldn't have any seasons. It would always be nice and warm and awesome, right at the equator and a little bit north and a little bit south of it. And then as the further north and the further south you went, it would be, that temperature all year. Again, adjusted for latitude. Latitude, by the way, are the lines that parallel the equator. Longitudes are the ones that cross through the equator. Okay, I've been using the word latitude a lot. Not sure everyone knows latitude. How many months are there? How many seasons are there? How many seasons per month is that? There is no math requirement for this class. There is no math requirement. Yes, 12 divided by 4 is 3, you guys. So, should be 3 months to a season. All right, where in the world do you find that? Well, a handful of places. And like I said, it's a latitude thing. Okay. Obviously, you go towards the equator. I'm sure they complain about it because they're tired of it being hot all the time. I don't know. But, obviously they see the other end of things that we see where, summer and spring stretch, fall stretches. What passes for winter may be shorter there. Okay, but where we are, winter stretches. And oddly, it doesn't come into the fall. That was one thing I was surprised, more so that it stretches into the spring. Because are your falls, actually, I've been here 20 years, I shouldn't say you anymore. Our falls are fairly like what I grew up with. It's the springs that are changed. So I don't, there's some fact I'm missing there to understand why winter lingers, but fall doesn't change. So. All right, again, any questions about this? This is a handful of questions on the test, okay? Now, it's horrible that it bounces from the 20th to the 21st to the 22nd. Blame whoever set up the solar system. On the test, I put them all at 21, okay? Just to make things easy on you. So all you really have to remember are the months. September, December, March, June. It's always going to be the 21st on the test. You'll want to try to remember, again, that 23 north is Tropic of Cancer, 23 south is Tropic of Capricorn. You'll want to remember where the sun is on the equinoxes. You want to remember where the sun is on the solstices. It does turn into a handful of questions, okay? And again, the reason for all of this is because of the tilt. Spent a lot of time on this slide, so there's a lot of questions. So again, I'll ask you one more time before we stop. Questions about this?
Yeah, but do these dates ever change in the year?
You know what? If I had the memory or the wherewithal to write it down, I don't know. I swear that, at one point I was convinced that it was always the 21st. But I do think that and again, don't quote me, that sometimes it does bounce around a little bit. Again, we're not in an even, we're in an ellipse, and I think that throws things off a little bit. We could just, again, ask Siri here. What is the autumnal equinox this year? September 22nd. I want to say I remember a few times when the dates. Leap year. I think leap year throws it off. I think.
Eventually it'll move days.
Yeah, it's got to, but
Because like time is pretty relative to delay, and it moves everyone's like days get moved.
yeah, because you got to cycle through seven years, I think, to make it come back to have it today. Like your birthday's on a Friday, you got to wait 7 more years, I think, for it to be on a Friday again, kind of thing. But I don't know that that's connected, but yeah.
25 planner is different for the Roman one. It's on the 19th to the 20th.
Okay. It's on the 19th. Wow. For 2024? Oh boy.
And then for the summer one, it's on the 20th.
Gonna have to go adjust Stonehenge now. But yeah, I mean, it's I don't know. I don't want to say I know a decent amount about astronomy. I know some things astronomically related, and I know enough to know that there's variability out there. Okay, to what degree? No. The good news is I guess right. Thank you. Good questions. What else? Well, I've crammed an awful lot of things into your heads. It's not too incredibly early, but we're switching gears again, so I think it's a great place to stop for today. So, and you folks at home, email me questions, okay? This doesn't have to be a one-way conversation just because you're off campus.